And our next speaker, actually, we have, I would say, three musketeers who are co-authors of the next keynote presentation. And the title, and then I'll introduce the co-authors. The title of the next keynote presentation is Electronics Quality and Reliability for Critical Applications that Adopt New Technologies and Designs. And there are three co-authors for this keynote presentation. Alan Lucero will be the speaker, but his two co-authors are also Ravi Mahajan and Joe Welchek. And here is a brief introduction of these three outstanding individuals. I'll start with Alan Lucero. He is the managing director of the Global Quality, Reliability, and Regulatory Standardization at Intel. He's also chairman of JDEDEC JC14 Quality and Reliability Standard Committee, and is the United States delegate and chairman of the International Electrotechnical Committee. Ravi Mahajan is a well-known person, of course. Alan Lucero is equally well-known, and is an Intel fellow responsible for assembly and packaging technology, pathfinding for future silicon nodes. Ravi also represents Intel in academia through research advisory boards, conference leadership, and participation in various students' initiatives. Dr. Joe Welchek is a principal engineer at Intel Corporation. Joe leads strategic technology programs in the Assembly and Test Technology Development Organization, where he brings 20 years of experience and insight on innovation implementation for quality and reliability in the high-volume manufacturing environment. So the speaker today is Dr. Alan Lucero, and let's welcome him. And again, he represents three co-authors, himself, Ravi Mahajan, and Joe Welchek. Alan, go ahead.
Great, thank you, Ephraim. So I'm here today. We'll talk a little bit about the electronics quality and reliability. And I recognize that there are a lot of folks from the optical area in this presentation. So what I've done is I'll adapt some of the slides to have that discussion. Essentially, the reason we are here is because we have modern societies that are used to and accustomed. I'm going to turn off the video now so that we can have the better bandwidth here, so that we can have cheap products with very good performance when and where we need them. So we usually use low-cost products to access a lot of the technology, and a lot of the heavy lift is really done in data centers and networking areas. And this will be the same also when we move to automated cars and various levels of automation in the factories through the Industry 4.0 sorts of systems. So we'll talk a little bit about that, and we'll talk a little bit about how we can take the existing tools and methods that we have and apply them and reach or respond to some of the new challenges with the new technologies that we will be introducing, such as those listed on the heterogeneous roadmap. Others include the silicon photonics area and various sensors that will be coming very soon. We'll talk a little bit also about the, very interesting, hold on just a second. We'll talk a little bit about the HALT and the HASS methods in the context of the presentation here. We can recognize that those are a little bit different testing, and we'll see how we can use them. So our talk is we'll show the motivation, which is partly what I've done here, the demand and the use environments, so what we will be designing for and testing against, And then we'll speak a little bit about failure-oriented accelerated testing. And this essentially is test of failure, as was mentioned in the previous presentation. And this particular verbiage was actually defined by Dr. Suhir here. And then the physics of failure models, specifically how we'll use some different sorts of failure models and look at the physics of failure. So my undergrad, part of it is in physics. So I may have a different view of this than your traditional folks in mechanics or in electrical, which dominate a lot of people in packaging and some of the semiconductor reliability. So I'll put that spin on it. Then there's the statistics and its implications, and again the discussion on the HALT test and the HAS testing. So the motivation that we have today is essentially that the electronics we use are ubiquitous, so they're all around us and they enhance our lives. We tend to access them with the short-lived mobile phones, tablets, or through gaming devices. There are other devices that are productivity devices that have a medium life, so we pay more for them and we expect them to be available more often. And the level of performance we expect to be somewhat higher. And then there are infrastructure and safe devices that are very long-lived, very expensive, and require that have different sets of requirements. So these are basically some of the devices that we'll be talking about today, is essentially the infrastructure and the safe devices. Furthermore, a lot of these devices these days are connected. So the first revolution was use of the PC to improve productivity. Once we could connect them, then we started seeing benefits of that connection in the digital realm, where you could have different devices speak to each other and it further improve productivity. And now we're moving into an autonomous and an inferred area where you're going to have those devices make decisions on their own and infer behaviors and essentially do things for us that we take for granted today. And that'll happen. A lot of that is going to happen in infrastructure devices and maybe aided in some of the access devices. And then the new technologies, we'll have some challenges when we come to these. Not only do we need to improve the performance, we need to lower the power. We need to use new technologies to lower the energy use and to increase the data rates. And that's where the silicon photonics, of course, also comes in. So we can interconnect between systems, between racks, and between data centers, and between continents. And we can speak a little bit about that. So all of these essentially speak to some part of dependability. And dependability, we will have a discussion of that in the next slides. So the dependability is most important for shared use and safety. So if we really want to have ubiquitous computing, and it's like utility, a telephone, you turn it on, it's there all the time and we don't notice, then we need to have a different approach and look at things from maybe a system level approach and then down to the component level approach. And then the reliability and essentially dependability, we have to design into systems and components a priori. This can't be qualify it and then improve. You have to understand the use a priori and design that into the technology. So that goes into every aspect of the decisions made for the technology you're using. So if you're using certain transistors, they need to operate with a certain performance. You need to know how they're going to be used in the end and what types of circuits that you're going to use them on. That allows you then to change doping levels and the gate lengths and materials from the from the atomic scale. And then when you move into the packaging level, you're going to pick different materials to accommodate the various stressors that come from the various temperatures or the various electric fields or these days maybe even magnetic fields. And then lastly, we want to have some quality and reliability estimators that are validated upon qualification. So this is basically a building process. You need to design in reliability, test for it, and then you need to test for the quality and make sure that those reliability estimates are all good. And we'll have how that flow works courtesy of my co-author Joe here. So again, another slide on the heterogeneous products that integrate many functions. And this slide's a little bit complicated, so I'll walk us through it. If you look at packages, let's say about 20 years ago, they were very simple. They came in a standard design and a standard layout. So you connected to a power with pin 1, and you had outputs in pins 5 through 8, sort of like that. That would be a standard design. When we moved into plastic BGAs and even starting with the PPGAs, we started to see some customized design. And with the plastic FC BGAs, we were able to then start optimizing electricals in the package to match or enhance those electricals that are needed by the silicon. So that interconnect and the optimization there became very important. We were then also able to start optimizing electricals and lastly, thermals in the package level. And as we go forward here into these custom designs, we're moving now into full design integration. So you have silicon or many pieces of silicon that are integrated onto a package, and maybe there are packages with many pieces of silicon in them. So you're nesting all of these various technologies in with each other. And you have various design integrations, and you have a lot of co-optimizations that are taking place there from the electrical level, the functional level, the thermals, and the mechanical levels that need to be dealt with. And these days we've moved from a logic or analog area from 20 years ago into where we've mixed analog, logic, memory, silicon photonics, and maybe even MEMS on the same package, depending on the application. So all of these require some level of quality and reliability, and they're used. We can also use that same information to develop the products and to assure that in the use environment and the expected lifetime that we hit those targets. So I've recycled this slide, but I think I'll give a kudos here to Professor Suhir. He was able to look at this slide and say, hey, I can derive equation for doing that optimization. He has a publication that was done on that we worked with him. But what we see is this slide tells us that we are looking at product cost and the cost of failure versus the quality and reliability. So if we want to sustain a high failure of cost and returns at a low quality and reliability, we can. Otherwise, we can start to do quality and reliability testing or design for quality and reliability and test. And the cost will go up. So the total cost essentially goes up as you start to add in more quality, reliability, and testing. And there tends to be a sweet spot somewhere in the middle. If you're in the far right-hand side, you're in a niche business. So you're in the 20-year lifetime business. You're in a military business. Hey, I only want parts that operate at up to 200, I guess 150 or 175 degrees C, and then minus 75 or minus 80 degrees C. And they have to operate. So that would be a very niche application. And those parts also would be very expensive, not only due to quality and reliability, but because there's no economy of scale. That's why people are going to the COTS, because you have economy of scale and they're widely available. Then on the other side of things, you have the stable return business. And there are some companies that have a philosophy is if I want to be first to market, I'm going to have to sustain a higher defect level or a higher level of reliability and work those down during the product lifetime. So depending on where you want to be in this curve, if you want to be in the absolute low part, you can be. Some companies are conservative and they want to be there and their customers need to be there. Other companies will say, hey, I have enough money and I'll just replace that for my customer. And the part's only going to last 3 years anyway. So there's a wide variation in this, where you need to be in this cost optimization curve. And the goals here, if you look at the high quality and reliability versus the balanced quality and reliability, you're speaking about an order of magnitude different in the goals. So there's really a big challenge for producers here to manage all of these at the same time without a knowledge of how parts will be used. Okay, so let's talk a little bit about dependability. Most of the parts that we are building these days are no longer discrete components. At an IP level, you've merged them onto silicon, so you have memory controllers that were before discrete components with a CPU or a GPU, now on the same piece of silicon in another area. That's one way to do integration, and then we've started to integrate different parts of the system into the CPU itself or into the chip itself, and then into the package as well. And all of these need a high level of dependability. So now that we're moving from component level in the design and availability of products, now we're having to think like systems level folks. And they've had this concept of dependability. And I've given you the definitions from the IEC because they're the official definitions, and they actually fit quite well. The construct that's here, I think that DKE, Andreas Alf from Volkswagen, has a fairly good construct there if you care to read his paper. But you see all of the elements of dependability here: the security and safety, availability, quality, reliability, durability, and recoverability. And it turns out that they're all quite related, and for instance, a robust technology has some level of reliability or extra reliability built in. So that can be essentially quantified and traded. How much do you want? The same thing with availability. Can I perform to specification at all of the temperature ranges? Or is there some level of failure or quality that I miss there? So when something does happen, can I recover? And that would be the durability. And can we design in features like RAS or soft or error correction to give us some level of resiliency or durability? So these are the areas of the dependability that we speak about, and these are the areas also covered by the FUSA, the functional safety guidelines for a lot of the autonomous vehicles and factories that are coming up. And they're all quite related to quality and reliability in many aspects. And they're very interactive. For instance, we can put in software that impacts the quality and reliability, or we can have software that impacts the resilience. So all of these are very interactive, and that's how we fit in. So getting into some more detail, one of the things that we need to consider during the design, manufacture, and testing of durable systems is, how we do this and how we do it so that we're successful, the first time, not by trial and error. With new technologies, you don't have the luxury of having 4 or 5 or 6 generations of silicon and 4 or 5 or 6 generations of package design rules to rely on. So you have to essentially understand things a priori. One of the ways you do this in the product design stage is you do design FMEAs. So that would be on the upper left-hand side. To do those, you need to understand the customer expectations and their uses. And you need to essentially use what you've learned from the previous processes and heuristics to essentially do a probability or probabilistic design for reliability. I don't get too much into that here, but the same tools that we use to predict reliability can also be used to predict what reliability you can get and do optimization in the design stage for the next products. Once we have a product that's designed, then we move into a validation area. So we want to achieve quality. That's the goal there. And we want to process some parts that are stable and capable. We're always getting the same silicon out that has the same performance and the same timing. We're getting the same package out that has the same thermals and same mechanical reaction. And we're able then to functionally validate that, and that's essentially the test scheme that we'll talk about. And it's very important for all of this essentially to work, because we use test in many ways, not only for looking for defects, but we also look at it for looking for functionality that's required by the reliability stress to update or understand the failure modes, or to identify the failure modes, which then can help us look for failure mechanisms. And then key to all of this is in the development area, we do the reliability stress to validate those things that we predicted by the FMEA, and to understand the operating limits of the materials and designs that we selected to validate that they're true, and to understand if there's any failure modes that we need to manage. Since it's a cost optimization, or in some cases on the silicon side, we're dealing with materials that are very exotic on the periodic table. So there's not very many materials left to go and look for to make things more reliable in some cases, or have more performance. You have to start changing how designs are done and organized to make the next level with some of these new materials. Once we do the reliability stress, we identify the failure mechanisms. So the reliability stress is the failure-oriented accelerated testing. This is the test to fail. We identify the failure mechanisms, and we establish a physics of failure. We can then start to think about, all right, what is the distribution, the statistics of how these failures occur? And that is a very large area, because we can talk about materials properties, but the truth is they vary. And so do the tests that we use vary. So we have to understand statistics and safety factors and guard banding for all levels, from the transistor level all the way through the package and thermal and system level. And then how do we use those for reliability prediction? We use the use condition, we use the models, and we establish what we should be passing to meet a specific or sets of use conditions and customer requirements. And then we can go on to qualification. Qualification is just a validation. You really don't do large enough sample sizes, and you don't have the time to do different other types of failure-oriented accelerated tests as well. And we'll have a conversation on the topic of qualification and the qualification types. So if I were to look at this from kind of a stress strength perspective, the reliability is essentially overlapping or interference of distributions. On the left-hand side, we have design quality. You want to design an operating range that's in between the demand and the strength. So you don't want the demand or the stress to exceed the strength in the operating range. You want to have some margin, and that's what the little black items are there. Turns out that properties and responses change as you go through life, so you're able to define reliability and hazard functions that where you start to see the demand overlap the capacity. And that interference then becomes the failure percentile. And there's been publication below that has suggested how you can take advantage of some of these optimizations to meet the stress versus strength, or the demand versus capacity optimization for individual failure modes. And I believe there's maybe some construct for multiple failure modes at the same time as well. Now, if we look at the HALT, the highly accelerated life stress, life test, and screening, these are a little bit different. We still have the operating margin in the middle, and you have for product spec in between that. But when you apply highly accelerated stress screen, you're starting to look at sort of the ends of the stress and the strength curve. And you should be able to find basically weak links or weaker areas in the stress area, or maybe there's certain aspects of a construction that make the stressing is a little bit higher, and the strength may be subject to process capability or materials variations. And we can speak a little bit about this, and I'll do that in the next few slides. I think the key thing is with the highly accelerated life test, you can inform technology, but if you use the HALT test in particular, you may have yourself in a difficult area to quantify the estimates of failure in life. And that's just because of the way the distributions change during the test life and the life testing. Okay, so the next thing is the failure mode and mechanism, and we'll just spend a few minutes here. Failure is essentially the failure to meet an operating or conforming spec it's detected by a mode. So when we do testing, we're looking for things, opens and shorts and IV shifts, insertion loss, for instance, or visual attributes. From those tests, there may be resistance or a parametric value that shifts. We may then extract the mechanism, which is the physics. What is the driving energy for failure? And that driving energy can be, chemical related, a flux, or a field related type of an energy that you're going to look at. And we'll speak to some of those, but this mechanism is key. So I've given this foil probably about around 2010, about 10, 11 years ago, and I've updated it slightly. I've changed a little bit of the observed failure rate slopes. But essentially, we want to be in the area of a decreasing failure, or in the early life, this is the bathtub curve, you're going to be in the area of a decreasing failure rate. And there are various ways to do that in the test environment before you build up a product. In life or in use, you'll be seeing a constant failure rate. That means that there's random failures that occur. Neutron hits might be considered a constant failure. Neutrons are always impacting the environment here, or alpha particles getting cascaded. And then lastly, you have an increasing failure rate, which is related to wear out. And these tend to be intrinsic related failures. So our goal and our challenge is essentially in all these areas, in the early life, to accelerate the early failures and to accelerate the life failures. And we do this by the failure-oriented accelerated tests and through the physics of failures models. So the role of test is very important. We saw that in the diagram there. And it's a scheme where we essentially screen for quality and performance issues. And the coverage in that scheme is typically defect-based detection. And we derive that from known or modeled structural and functional fault modes. And this can be considered a way to do HATS, highly accelerated stress screening. And the way that we would do it from a new technology development point of view is we would start with wafer level sort or testing there. You can apply a stress at wafer level before parts go into assembly and start the screening there. And that could be a structural test, or it could be even a reliability test in line in the wafer process. And then you move into assembly and you're going to do some more testing and more burn-in. So you'll do another structural test, another burn-in, and you're going to find more failures. And those will be latent failures. After that, then we'll move into classification test. And then subsequent to that, you can validate all of this on a system level test. So these days, we do stressing at the wafer level with what we call a high voltage quick kill, which is essentially a way to increase the voltage at a wafer level on an individual die level. And we can do it at hot or cold temp, depending on the failure modes we're after, and start the screening from the very beginning. What this is leading to is essentially an interleaved screening process from the very beginning of the metal layers all the way through to package assembly and out into when you have a product. And the test content becomes evolves differently depending on part of the process you're in. So this methodology needs to be pretty robust, and we need it to meet demands of the future package architectures, which I'm going to show you how it plays out in the next slide, a little bit more complicated. We know that a lot of the heterogeneous, there's many reasons for moving to heterogeneous architectures. One of them is high defect levels or high failure rates on large pieces of silicon. High defect rates on many pieces of silicon when they're all combined. So one way to mitigate the effects of high defect rates or the low yield, if you see the 16 die case on the right-hand side, the most extreme percent, the defects out of wave per test, let's say it's 2%. Your yield loss on a complete product can be very, very high. And that's really something that you don't want to have. You're going to lose very good silicon, and you're going to lose time and money that you've spent to put all of these various pieces together of parts that you've purchased from other companies. And you can see that in the example here. One way to do this for heterogeneous applications is we can treat all of the wafers like we've treated them on the previous slide, where you have the progressive defect screening and testing. And when you apply those together in assembly, you can again do your normal testing and do again testing at the final product or system level there. So what we have to do is essentially take all of these known good die, apply the testing at the wafer level, and the stressing at the wafer level, and continue that process for all the known good die to result in a high yielding and a high reliability heterogeneous package that's fully integrated. And this really drives a lot of test challenges. There's a lot of test content that needs to be modified at the various areas. And then once you identify failures, we have to understand why they failed. So that drives a whole new set of tools for analysis of failures and determining failure modes and mechanisms. So reliability essentially uses those structural tests and functional tests to help us understand the types of reliability testing we do. So the reliability test challenge is to mimic failures in time that occur in lifetime. And you can have a live test, you have no acceleration there. You can have an accelerated test, you don't want to induce any artifacts there due to the testing. And then you can have a highly accelerated stress test beyond the capability of the normal stress or strength, where it can give you some information. I think the optimum that we need to be in is in the accelerated live test, so we understand what we're doing. Okay, I need to move very quickly because I need to go through some meatier content. Next one that we need to look at or understand is the use conditions. Use conditions vary by segment. They also vary by software. These days when we use AI software, even the versioning of the AI software can be adaptive itself, and it changes the use pattern, which results in a change in temperature to a package in a system, and you may get a different electrical loading as well. So the use conditions also can be dynamic in many, many ways. But if you start to look at the statistics of them, then maybe you start to see patterns emerge. And that's what we see. I'll let you read through all of these, but the various differences are, you can see maybe a laptop is dropped, so is a cell phone. Maybe a PC is not dropped, but it experiences more wide temperature variations. So it gets pretty complicated, but you can start to decouple all of these various ways the use environment affects the part. And you can look at it sort of in this fashion. You can look at a storage area, a shipping area, how a part is used, so because parts are variable. And then with the user transport area. And once you study these, you find that shipping and storage is pretty common. That's an environmental factor essentially, and the population, the Earth is in a small temp window. The user environment changes quite a bit, and then software can impact that somewhat. And then the user transport doesn't change much, and the ambient environment is represented also by the climatic data. But we really need to work on the CD and E areas. Turns out that they're not not discrete values. They turn out to be probabilistic in many ways. You can make, in the shipping and storage, you can make those discrete and deterministic values. But in use, you see a wide variation of the temperature and ambient conditions. And then if you start to add in, software and system variations, you can see even different sorts of variations. So the use conditions essentially are not simple, and they're not discrete. They're population-based. Here's an example of some work that we do. In Intel, we can monitor a lot of our own systems internally. Here we have a sampling of around 5,000 systems. And we can estimate the amount of what's called P0. So this is essentially full clocking in one day. And you can see some systems are at 90% full clocking for a full day, but the vast majority of them, over 95 percentile, are probably less than 20% full clocking in a day, in a 24-hour period. You can also do the same thing for off time or humidity exposure, and you can look at various data for the same thing and apply a different model and find out what kind of moisture concentration you're dealing with when you're doing designs, selecting materials. And you can do the same thing for a number of cases as well. And what you need to do is figure out where you want to be on the probability curve, because you can always design for the worst case, 99, 6 or 9. But if it never occurs, then you will have spent your money on exotic materials. Okay, I'm going to shift quickly into the qualification requirements. So one of the things that we do is we need to understand the customer demand and the use case that they have. This really drives what we do. So if we want to use a part in an airplane in avionics, it probably is better to understand that environment and design for it than to repurpose a part, because that comes with other risks. There's competitors we also have to be concerned about. Does a competitor offer a better product, and can we get the same thing? So that's another thing that we need to worry. The capabilities, can we achieve this? Can we have a process that can do what we need to do it? And then what is the engineering? What is the cost? Can we make money in this market? Or is that just a niche product and we have to raise the price? These are the insights that we need to consider also with the design. And these are not the same level as engineering quantification, but you can put a number to them. So there's two types of qualification in the end that can be done. One is a stress-based qualification, which is essentially buying into a used or assumed use case in an assumed environment from history that then has been tabulated. And we do this all the time. All of this is the JEDEC standards for stress-based qualification, telco standards like Telcordia. These are based on use conditions and cases maybe 20, 30 years ago. That's the stress-based qualification that we're qualifying to now. And because we use legacy packaging and silicon technologies with a lot of history, we're comfortable with that because we get a cheap price out of it. If you're going to use new technology, then you need to understand the failure modes, physics of failure, and design for the use environment. And that requires, from the very beginning, to insert in the FMEA the heuristics as well, but also insert the physics of failure models to make decisions about how you design. Those that go into EDA kits that then also test or estimate reliability in design in the physics, using physics of failure models. When we develop technologies, we validate those physics and models. We then do the testing, failure-oriented testing. And we define failure statistics. So what are the ranges of materials properties used? What are the ranges of variations in the test that we use? All of that goes into that testing and characterization. We can then maybe tweak some of these things and improve the design. And then finally, we can match the design rules and the expected user environment and then release a KBQ report for a sample environment. And then you can go on and test those in the use environment, and you can do the qualification as a test to pass. So you get a reasonable sample size. And then you can also do the test to fail also. So you do that at a higher confidence. So stress qual is a benchmark, but it doesn't tell you much about the quality and reliability. It tells you you've achieved something that maybe is similar to what you know. Knowledge-based qual requires a lot of information, but and it requires the FMEA to have considered the potential failure modes quite well. And then you can establish the limits and the testing requirements. So what are the stimuli that we look at? Here's a listing of a number of ways. So remember, we said we were physicists. So we're going to look at what drives failure. And all of those stressors or stimuli are on the right-hand side. So any one silicon and one package has essentially all of these that are considered and in all of the use areas. So we look at the IM, we look at extrinsic defects, we look at the wear out. So these are all of like hot carrier or solder joint cracking or inner layer cracking. And in the constant area, there's the soft error, right? So we're able to consider all of these in design and in simulation.
5 minutes, Alan.
Okay. So here is a case where we have a silicon process that was changed, and we didn't pass the 1K hour of HALT, which is a standard from let's say 20 years ago. However, the lifetime that we estimated was 2 to 3x the lifetime of the legacy product. The reason this was different is because the voltage acceleration and activation energies were different. So when you change the technology, then you need to reconsider the models and the acceleration factors that you use and the acceleration model factors. And if we would have just done the stress-based test without understanding of failure, we really wouldn't have many of the technologies we have today. This is a THB requirement in red. If you have like tin whiskers and corrosion current testing today, won't catch those because the acceleration factors are too small. So you really have to consider your stress-based qualification. And the same thing applies here for the temp cycle. If you take a model, Coffin-Manson, for instance, that has certain assumptions in it and certain simplifications. And if you follow that model, you might have a technology that fails, but it passes in the use case. And it passes maybe in a more rigorous environment, a set-top environment, but it would fail in the qualification, the stress-based qual test. So you lose optimization, you lose markets. So how do you do this probability for design testing? You start with the use condition, you do the testing, you develop the physics of failure models and the prob design. And I'm going to move through this real quick. This is an example. This is a tempo cycle one that folks understand. And we can all buy into the fact that really strain is the metric that we can look at and compute stress and understand that accumulated stress to fail. Okay, and that's something that we can do. So previously, you know, we can use a Coffin-Manson equation and think that we're doing reliability, but we're really not. The best thing to use is the cumulative peak, creep, and fatigue damage model, and this can allow you to do essentially predictions at various use conditions and different geometries rather than the one geometry that you've been testing all the time, which we're changing geometries every day. So we need to do this. The common Coffin-Manson model that's used in temp cycling, all I'm going to say about this slide, and you can look at it afterward, is we've simplified it to call delta T equal to strain. And that's probably not the case. And I have a few examples. One example is this case, where you have a different failure mode that's not related to stress and to the creep and the stress, fatigue, but maybe a more brittle fracture. And so delta T is not the one to look at. You need to use that strain, and you need to probably turn it into a critical crack growth energy. And there are various ways to do this. Do it through simulation, finite element models, but you can also do it through scaling models. And some of the papers we've done in the last 5 to 10 years have given the same result as a scaling model, although the units are different, because we can solve them without using finite element. But they're very good for design implications and real stress to fail. So I'm going to move through that one. Using contemporary computational models, we can take that actual temperature use condition, put it in the physics of failure model, change it and look at the use condition to test condition relationship, and we can do customer design tools, or we can tell performance of that part. That we can include thermal gradients, glues, basic loads in the test environment in all of these models. So previously we would have done just a number of cycles, and we would come out to some kind of a test requirement that doesn't mimic what happens in the real use in the power cycle case. But if you want to do telemetry and actually measure the temperature profiles on the right-hand side, you can compute transient temperature fields. You can then compute solder joint damage. You can have a master curve that shows you by geometry what to expect, and then you can come up with a requirement. And in this case, the requirements were probably 6x different than what we were doing in the past. They were quite a bit lower, and what this enabled was a thinner and a smaller package that particular customer wanted, and it reduced BGA counts and complexity. So, the benefit of doing that was cost saving, but it was also the smaller package that the customer wanted at a reduced complexity on their part. You can then also do this from a statistics point of view. So if I were to look at a number of parts at Intel, I think there were thousands here, I can start to look at different systems and how they all perform and estimate what their level of damage is as they go through their lifetime for the various models. And I can even find outliers based on their telemetry. And that allows us then to basically optimize and then look at that goal and determine what would pass or fail in the next set of requirements. So I'm going to look at, again, the HALT test. HALT is shock or vibe events in a chamber that's at temperature and could be with moisture. I would argue that that's an arbitrary test, and you can only tell performance on some configuration exactly the same as the last configuration you built. So if your board is a different size or your system is a different size, the response inside that system is going to be different, and the response, especially at the solder joints where you're concerned about, are different. So you can essentially compute and understand through strain measurements and computational means what kind of stresses you're imparting, and you can essentially come up with some kind of a stress. If you can measure that stress and model it in time and validate that stress applied over that time is good, then you should be able to then optimize the stress distribution. And you should know when you'll fail, and you can design that way for a particular environment. And then set your requirements. So previously, we would have just measured board strain and made sure all the components stay below board strain. But it turns out that that board strain by itself, because you can measure it, one is there's variation to the measurement, and the other one is variation in the systems that it goes into. It's kind of useless as a metric. The best thing to do is measure the stress, and then you can measure how people are, or understand how people are doing their designs to manage that stress. And that's what we've done here. You can find a safe zone essentially for a current dynamically applied stress. So this really turned from a HALT type of a test where you were looking just to break something into something where if you do the work, you can dig in and you can find out how you can apply it to different geometries and elucidate how you can do better designs. So summary is that we have all of the requirements or elements for a probabilistic design that we've shown. We gave some examples of the failure-oriented accelerated testing, and we compared the ways to do qualification, knowledge-based versus stress-based, and then lastly, what can we do with the highly accelerated stress testing? And silicon photonics is a new area. There are not very many models created for a lot of the silicon photonics. There's Telcordia, which is a stress-based system level model. But if you look at it from the silicon wafer level and the integration into a module, you don't have very many existing stress test models, and that can be applied to a known use condition. We don't know the use conditions as well. So all of these principles will have to be applied as we develop standards for silicon photonics. And that's silicon photonics standards are those that we're developing right now in JEDEC for wafer level silicon photonics. And then you integrate them into packages and modules, and that's another set of models. So that doesn't exist for that area. Any questions? I've rushed through the last part here.
Thank you.
Thank you, Alan. This was wonderful. That was a very in-depth presentation.